Get it? All right. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. We thank you for the break, which we just completed. Just ask that you be with us today. Help us to, again, Lord, glorify you and what we do here. In your name I pray, Lord Jesus. Amen. All right, so there's a bit on Hodge theory, well, not Hodge theory, on de Rham cohomology at the end of chapter, what is it, 6 or? Yeah, 6, de Rham's theorem in section 6.5. And here he describes this notion of a period. Basically, he looks at this sort of duality between chains over a manifold and differential forms, right? And basically, through integration, he builds this mapping between the set of chains on the manifold and, say, the set of differential forms. And so doing that, he establishes this mapping between homology, or more singular homology, and the cohomology, which was formed from taking quotient spaces of forms, right? And the ultimate punchline here is pretty awesome. It's simply that, this theorem 6.8 from de Rham, it says, let M be a smooth manifold. Then the de Rham cohomology coincides with the smooth singular cohomology of M, which is very nice. That's not the punchline, actually. That's part of the punchline. And then getting to the actual punchline, the corollary 6.10, he has that the Lth de Rham cohomology over M is isomorphic to the Lth homology over M. Now, so in some sense, this justifies us dropping that homework problem, because I had you guys calculate the homology of the sphere by looking at the chain complex over the tetrahedron, right? And the other problem I had assigned but dropped was to calculate the de Rham cohomology over the sphere. This theorem says they match. So if you've done one, you'd already done the other one. So you don't feel bad about not doing that homework. That's my point. You don't look too enthused. It's too. Oh, okay, yeah, they are in the later homework. Now, to prove this corollary 6.10, there's a page of diagram chasing, right, which is something I'd love to teach, but it's just not part of this course. So I will behave and not do it. But then the other contribution Hodge has for us is in section 8.9. So section 8.9 is obviously in chapter 8. Chapter 8 is on Romanian manifolds. So what is in brief a Romanian manifold? So we're working towards section 8.9, which is on Hodge theory. But just to preface that, he assumes that M is an n-dimensional compact orientable Romanian manifold without boundary. You could say this: the boundary of M is the empty set. All right. Now, so I guess the question is, what is a Romanian manifold? What does that mean? So, I've really just showed you guys the rudiments of manifolds in this course, just touching on it really. But you can talk about different kinds of manifolds. So you can talk about, like, for example, a Romanian manifold. You can talk about a symplectic manifold. You can talk about contact manifold. You can talk about complex manifolds. You can talk about there's all kinds of different particular types of manifolds. And these other types of manifolds, it's like what we've already talked about, the basic structure plus something extra, plus some extra structure. Romanian manifolds are probably the most famous, well-studied version of a manifold. The Romanian manifold locally has the Euclidean metric, essentially. So the Romanian manifold is basically M paired with something like G. I'll write a formula for it, a local formula for it, something like this. Sum over I and J, Gij, dxi tensor dxj. Now I could rewrite this in terms of a symmetric tensor because we're assuming that this is an inner product. Well, I really should say this g at the point P, right? So many P's, stupid P's. Inner product on the tangent space to P at M. And I mean inner product in the usual sense, like it's positive definite, it's symmetric, it's bilinear. You can choose a system of coordinates where the matrix of it is the identity. Through some sort of Gram-Schmidt process, if you want. So that's the context. That's what a Romanian manifold is a manifold paired with a metric. That means we have a way of measuring distance and angles between curves and all the usual stuff. You could take a whole course on Romanian manifolds. So I'm just giving you the start of it. Study geodesics, so forth and so on. Now relativity is built over what's called semi-Romanian geometry. Semi-Romanian geometry, a semi-Romanian manifold, instead of pairing it with an inner product, you pair it with like a pseudo-inner product, or what we call the metric on each tangent space. You have something that could have, it could have some of the, it has to be non-degenerate, but you can have the metric of a vector with itself be negative. You have these metrics with, anyway, like Minkowski space, for example, is an example of a flat semi-Romanian manifold. All right, and there's whole books written about semi-Romanian geometry as well. Okay, but that's really the geometry of general relativity. All right, that's just a little bit of background for you guys. But so if we have some kind of orthonormal basis, so let's suppose that theta 1, theta 2, theta n is G orthonormal. And basically just that just means that these are covectors, all right? So I mean they're dual. Well, anyway, we talked about how to induce a metric for the cotangent space, and so in that sense they're orthonormal in the same way we talked about before. That really kind of somewhat beside the point here. We can define Hodge dual, right? Hodge dual. How do you define the Hodge dual? Omega wedge mu is equal to G of the Hodge dual of omega comma mu times sigma. Now here, sigma is just theta 1 wedge theta 2 wedge theta n. All right. So this defines Hodge duality, much as we did before. And so then what we do is we define a inner product on the exterior algebra. Over M. In particular, we take, say, eta and lambda, and we say that that's equal to the integral over M of eta wedge Hodge dual of lambda. All right. Now, of course, by definition of Hodge dual, that's the integral over M of G of eta lambda sigma, right? Where sigma is the volume form. Now, I will say this G, quote unquote, of eta lambda, I am abusing a notation following Rentlen. That's not the same G as this G, really, right? This is the G which is induced on the space of forms, as I spent like a whole lecture trying to unravel. I called it like G tilde upper P or something in a previous lecture, that thing, at a point. Now, we're not doing it at one point. We're doing it on the whole manifold, and then we're integrating to get a number. So we're taking differential forms. Now, what's the degree of eta and lambda in the formula I just wrote? So this is a P form. Let's say this is a P form. So this is what? still P. What's this? It's the Hodge dual of a P form. It's a n minus P form, right? So this makes sense. We're integrating a n form then. The wedge product of those two things is an n form. That's an appropriate thing to integrate over an n-dimensional manifold because it's an n form. So we integrate this form over this manifold, and we get back a number. So at least it's the right kind of thing. An inner product should take in two things from the vector space and give you back a number, right? How do I know that that integral is well defined? That comes from this topological assumption right here. Compact. That's what we need to make the integral manageable. Now, the second proof of the Stokes theorem, which I didn't cover in class, discusses kind of a different idea, which is that you could you could work with compact spaces. The other thing you could do is work with like non-compact spaces, but work with functions that are basically only non-zero on a sort of compact space, so-called functions with compact support. A function with compact support is only non-zero in some sort of compact region, and then outside it's zero. So you could integrate things like functions like that, functions that are basically zero outside some compact domain. You can also do integrals of those things. That's another thing you could think about when you take a course that's more serious about integration. Now, anyway, so that's a good definition, right? Is it bilinear? This formula, is it linear in eta and lambda? Indeed, because the wedge product is linear, right? Is it non-degenerate? I think you can see it's going to be non-degenerate because this is non-degenerate. In short, it's really going to steal the properties of the induced metric G. It's also symmetric, right? Because if I flip eta and lambda, well, I get G of, we proved that this was symmetric before. So all the work we did before for the G tilde P, it comes and pays off now. All right, so there's an inner product, right? So what? At this point, I don't think that the train of thought. We start another train of thought. Okay, we're going to use this. I had to introduce it, but that's okay. Definition. Coderivative. Coderivative. Delta is a mapping from K forms to K minus M, K minus 1 forms over the manifold, right? And how do you define it? Delta of eta is equal to minus 1 to the nk plus n plus 1 Hodge dual differential as an exterior differential. Hodge dual eta again. The notation here really gets kind of... I do get tired of writing this star, guys. I will admit. In my own work, I tend to degenerate into just using an asterisk for that. It's part of the reason I don't like to use asterisk for push forward. I can get away with the pullback being an upper star and the Hodge dual being a middle star. If I also had a lower star for push forward, I get lost. Too many stars. Nah. Okay, so can you do the counting? We take in eta, which is a K form, right? The Hodge dual, what is this? The Hodge dual of a K form is an n minus K form, right? And then what's the differential of a n minus K form? It's a n minus K plus 1 form. And then we take the Hodge dual of that, what do we get to? An n minus K plus 1 form, which is also equal to, K minus 1 form. So it's kind of the counterpart to the exterior derivative. It goes in the other direction. Okay, so this is actually the adjoint to the exterior derivative with respect to the snazzy new inner product we just found here. So theorem eta a k form on M, lambda a k plus 1 form on M, then d eta comma lambda is equal to eta delta lambda. Again, this makes delta an adjoint of the differential with respect to this inner product. With respect to the usual inner product on Rn, when you do this, basically if you have a linear mapping with matrix A, its adjoint has transpose, as it happens. But anyway, there's a great section earlier in Rentlin on some of the finer points in here, so I'm not going to dwell on what adjoints are today, although I was tempted. Okay, so here's the proof. So what do we got? 0 is equal to the integral over the boundary of M of eta wedge the Hodge dual of lambda. Why is that? What did we say about the boundary of M? The boundary of M is an empty set. The integral over an empty set is defined to be 0. So that's just an identity, given our assumption. But thankfully, Stokes theorem, generalized Stokes theorem, applies here. So I can trade this integral over the boundary for the integral over the bulk of the exterior derivative. In other words, the integral over M of the differential of eta wedge Hodge dual of lambda. But now I can use a product rule, right? Product rule gives me integral over M of d eta wedge star lambda plus minus 1 to the k, yk, because eta was a k form. So the product rule for the wedge product in the exterior derivative gives me a minus 1 to the k. I get eta, oops, I just pulled it out of the integral. Integral over M of eta wedge the differential of the Hodge dual of lambda. All right, so take a second here, smell the roses. What is the first term? See, this is exactly the inner product of d eta with lambda. So now we need to take this thing apart, all right? So to do that, I'm just going to calculate the exterior derivative. I'm going to work over here and then come back there. The the coderivative of lambda is minus 1 to the n times k plus 1, because it's a k plus 1 form, right? K plus 1 form, plus n plus 1. Hodge dual, exterior derivative, Hodge dual, lambda, right? So if I look at eta inner product with delta lambda, what do I get? I get this factor, minus 1. Oh, by the way, can you simplify this a little bit, right? If n times 1 is n, plus n gives me 2n, but minus 1 to an even power is 1. So we can drop those n's, and this just gives us minus 1 to the nk plus 1, right? Minus 1 to the nk plus 1, and then integral over m of eta wedge Hodge dual of what? Hodge dual of d Hodge dual lambda. Now, one of the Hodge duals came from the, so let me underline where things are coming from. So this is coming from the coderivative, right? This other one is from the definition of the inner product. Now, as we were talking about earlier, Joe, unfortunately, I wish it was always the case that the Hodge dual was just back where we started again, but it just is not the case. So, generically speaking, the Hodge dual of the Hodge dual Hodge dual of the Hodge dual is equal to minus 1 to the p times n minus p. In this context, this assumes we're in Euclidean case. In other words, the signature of the metric is 0. There's no subspace on which the metric can be restricted to a negative definite bilinear form. It's just a usual metric, and so when you look at the formula for the Hodge dual, it simplifies back down to this for a p form on an n-dimensional space. Now, all right. So in order to use this identity, I have to figure out what form am I acting on, right? So, okay, I'm acting on this thing, right? This is a p equals to what form? Let's see here. Can you guys figure it out for me? Lambda is a k plus 1 form. So I get a n minus k plus 1 plus 1 form, right? Which is equal to n minus k, right? Because I get minus 1 plus 1. Okay, so that's an n minus k form. So, all right, so what I have then is I've got minus 1 to the nk plus 1 times minus 1 to the p times n minus p. Maybe I can write that out, though. What is p? P is n minus k. Yeah, times k, times n minus n minus k, right? Yeah. Integral over m of eta wedge the differential of the Hodge dual of lambda. You lived a good life, but you're done. Oh well, it's a bad day for throwing markers. Oh, I know, I'm getting worse, I think. So I need a break. I need a long break. It's okay. Okay, so you can solve for, therefore, the integral over m of eta wedge the differential of the Hodge dual of lambda is just equal to minus 1 to the nk plus 1 plus n minus k times k. That's what this term is, right? I'm not there yet. This term right here is this term, and then I'm just solving this equation here for that. All right? Does this simplify at all? Yeah, we get 2nk 2nk minus k squared plus 1. Okay, great. So I come over here, and I get d eta comma lambda from the first term plus minus 1 to the k times minus 1 to the apparently 2nk. Oh, but 2nk we can drop, right? So minus 1 to the 1 minus k squared eta delta lambda. And so I get d eta comma lambda plus minus 1 to the, let's see here, so k times 1 minus k plus 1 eta delta lambda. Music. Interesting. Away in the manger, huh? Ooh. Interesting angel picture. All right, this is not a math book. All right. Okay, so this is the product of consecutive integers, which is necessarily even, because it's either even times odd or it's odd times even. Anyway, it's even. That goes to nothing. So you got minus 1 to the 1, which is minus, which shows you that this minus that is equal to 0, and we're done. Number theory test problem. Yeah, number theory test problem. That's right. That's right. Now, is this calculation super important in the big scheme of things in this course? Not. I mean, perhaps not. But I think this is a great calculation to show you guys because it's something interesting. The content of this statement is actually something interesting, and all the calculations we did kind of give you more practice with tinkering with Hodge duals and thinking about form degree and so forth. It's a nice calculation. All right, from this, we now define our next toy. The next toy is triangle, which is the Laplace Theorem operator, according to Rantlin. You might just call it the Laplacian, I suppose, up to a sign anyway. It's d delta plus delta d. So this is the Laplace Theorem operator. A few definitions for us. D omega equals to 0, omega closed. Delta omega equals to 0, omega co-closed. Oh, by the way, what are the properties of the coderivative? I didn't really tell you. The coderivative behaves very much like the exterior derivative. Many of the properties that we wrote down, there's a product rule. It's also the case that this has delta squared equals to 0. All right, that kind of, you can almost see it from here because you're going to get 2 d's, and it's going to be sandwiched with the double Hodge dual, which just evaporates to a sign. It's basically plus or minus d squared is the Hodge dual with some extra, with some extra Hodge duals dancing around, but it's going to be 0 because d squared is 0. Okay, so anyway, delta 0 is delta of omega equals 0 is co-closed. Next to the differential form co-closed. If you have the Laplacian of omega equals to 0, then omega is said to be harmonic. So this is what a harmonic form is. All right. And okay, so look at that for a second. What's the connection between closed, co-closed, and harmonic forms? Certainly, it's clear that if you have omega, if you have d omega equals to 0, and if you have delta omega equals to 0, certainly this implies that triangle omega is equal to 0, right? In other words, closed and co-closed implies harmonic. So then the natural question is, how about the other direction? Is that also true? So let's look at that. Assume, I guess I can do it here. Assume that you have a harmonic form, right? Consider, let's see here, what am I going to consider? My paper go. Let's consider 0 is equal to the inner product of the Laplacian of omega with omega. Right? Because if this is the 0 form, the inner product of any, inner product of a 0 vector gives you back 0, right? That's non-degeneracy in part of. Well, it's not non-degeneracy, but it's part of the bilinearity, of the inner product that gives you that. But of course, this is what? This is, it's d delta omega plus delta d omega, using the bilinearity of the inner product and the definition of the Laplacian, right? You guys with me? Now we can use this theorem, right, to trade d of delta. So the first one becomes what? This is delta omega, right? By this, I can, to move the d to the second slot, changes it to a delta, basically, if you want to think about it operationally. And here, this, of course, is, I can change this to what? This is, what is that? By the same token, if this is equal to delta lambda eta, and this is equal to lambda d eta by symmetry of the inner product. So I can also move the delta to the other side and get d omega, right? But what does that say? 0 is equal to something non-negative plus something non-negative, 0, right? So these two terms must be separately 0. And what's that say? By the by the positive definite property, that implies that delta omega is equal to 0 and d omega is equal to 0. So in other words, harmonic implies closed and co-closed. Now what this means then for the de Rham cohomology is that harmonic forms are playing a special role. The harmonic forms, they're somehow connected to the closed and the co-closed forms in this way, right? There's something interesting going on here. Let me tell you what it is. So this is the basically the punchline. Well, maybe it's almost the punchline. I don't know, maybe debatable. Maybe this is the punchline of the section. I'm not sure. What do you want to say? Oops, I should have kept that preamble. We are still assuming that M is compact, orientable, manifold without boundary. And here's the theorem. It's the Hodge Decomposition theorem. So let M be as before. Oh, compact, orientable, manifold without boundary. Any K form any k-form on M can be uniquely decomposed as omega is equal to d alpha plus delta beta plus gamma, where, let's see here. Of course, d alpha is what? It's closed. Delta beta is co-closed. And gamma is harmonic. So you can take any differential k-form and decompose it into a sum of these three things, and uniquely so. To prove uniqueness isn't too bad. Because of the linearity properties of everything involved here, if we can prove that the only thing that's zero, if we represent the zero form, it has to just be the components are all zero. That implies uniqueness, basically, right? So basically, it's kind of like an equating coefficients idea. So let's say 0 is equal to d alpha plus delta beta plus gamma, where, let's see, alpha is what? We could do some counting here. If omega is a k-form, that makes alpha a what? K minus 1 form, right? Beta is a what? K plus 1 form, right? And gamma is a k form, right? Now, we're assuming what, though, with it's harmonic, okay? The fact that this is closed and that's co-closed is built into the expression, yeah. Nothing more. D squared equal to 0, delta squared equal to 0 gets you the co-closed and the closed. All right, so basically to prove that, I want to prove that d alpha, delta beta, and gamma are separately 0. We played pretty much the same games we were just playing over there. You'll use the inner product to pick off components, essentially. So, let's see here. So what I do is, following Rentlen, if I take the differential of this, I get 0 is equal to d alpha plus d delta beta plus d gamma, right? But, of course, this is 0. And so that gives me that, and what else is 0? How about d gamma? Remember, we just argued over here that if it's harmonic, then it's closed, so d gamma is also 0. By our previous work over there. That's not an entirely trivial calculation, but there it is. So you have d delta beta is equal to 0. So what do? You look at the inner product of d delta beta with beta. Now that's equal to 0, right? So 0 beta is equal to d delta beta 0, d delta beta beta. Now this is 0 by non-degeneracy of the metric, by linearity in the first slot of the metric. Inner product, I should say. And then we use the same song and dance as usual. This is what? This is delta beta, right? But by non-degeneracy of the inner product, that implies that delta beta is equal to 0. Then likewise, you take the coderivative of the 0 form. The coderivative of the 0 form gives me 0 is equal to delta d alpha plus delta squared beta plus delta gamma. The delta squared is 0. The harmonic form is co-closed, so those are 0. So we get 0 is equal to 0 comma alpha, which is equal to delta d alpha comma alpha, which is equal to d alpha, which is equal to 0, which implies that d alpha is equal to 0. All right. So we got delta beta equal to 0, we got d alpha equal to 0, and then it follows immediately from algebra, gamma is equal to 0. All right. So that proves uniqueness. In other words, if there exists an alpha, a beta, a gamma, which reproduces omega in this way, they're uniquely given as such. All right. But the question remains, how do you know that there even exists one solution to this? And this is a differential equation, right? I mean, I don't know if you can see this or not, but it's a rather formidable differential equation we're facing, really. So let me state the differential equation as carefully as I know how, given our language. So here's the problem. Given a k-form, omega, right? So that would be something like omega I dxi, right, in local coordinates. Sorry, my physics is showing. There we go. There, okay, I fixed it. Sum over I. Given a k-form omega, that's given. The coefficients of omega I are known, they're given, right? Find alpha, beta, gamma with omega equal to what? Well, there it is, d alpha plus delta beta plus gamma, such that the Laplacian of gamma is equal to 0. Now, when you write this out, this and that together give us a system of PDEs based on, the omega I coefficients, right? And the definitions of the derivative, the coderivative, and the Laplacian. At this point, Rentland punts and tells you to look in another book. He says, it's an elliptic partial differential equation. You get second order because the Laplacian second order, the other derivatives are first order. I mean, the coderivative and the exterior derivative, these are both first derivatives, plus some algebraic machinery, but they're really first derivatives, right? Whereas the Laplacian is a second order, right? And the leading order determines the type of differential equation it is. So since the leading order is, in terms of the Laplacian, which is your quintessential elliptic PDE, well, there's this existence theorem for elliptic PDEs, which says solutions exist. So it has a solution. But that's really not, that's a problem for your graduate PDE course to properly attack. All right. In the universe of my lecture notes, this is one of the things that's missing, is a proper discussion of the existence theorem of ODEs, PDEs, and such. So sorry I can't go further on that, but I will give you an example of what this means. So consider application. What if you have, say, the work form of a vector field? What does this theorem say? It says that you can write it as what d of, so if the work form, this is a one form, right? So we take the exterior derivative of a zero form, a function, let's say phi. The coderivative of what? A two form. What's the natural way to write a two form? How about a flux form? So application, I'm using R3, okay. the flux form of some other thing, let's say G. Now harmonic forms, interesting harmonic forms really stem from interesting topology, geometry. So the harmonic forms on R3 I think are just, what's a gamma have to, I think gamma has to be, because R3 is R3, gamma 0 or a constant. I'll just, plus a constant is actually. So I mean, if you're solving the equation, so the Laplacian in R3 is just this. As it acts on functions. So you solve this on a function equals to 0. What are the solutions on all of R3? I don't know. I have some uneasiness here saying that that has to be a constant, but oh well. I'll leave that as an open worry. But you know what you got here though is what? This is the so this is the work form of what? This is the work form of the gradient of phi plus what? This is actually the work form of the curl of G when you work it out. And so what you get is this result that a vector field F, and admittedly there's some reason we can take C equals to there's a reason I can take the gamma to be 0 here. I don't, that's the part I don't have pinned down yet, guys. I'm sorry. But there's some reason we don't need the gamma, right? Maybe it'll come to me later today, I don't know. But the F then is the gradient of phi plus the curl of G. In other words, any vector field be written as a sum of a gradient and a curl. This theorem or theorems like it are known as Helmholtz's theorem. Well, in Calc 3, it's a related theorem, see Helmholtz theorem. I'm hoping to teach that a little bit later today in Calc 3, actually. Oddly enough. All right, and then one last thing on this Chapter 8 stuff. Poincare duality. Yet another labor-saving theorem in terms of our calculation of cohomology. Poincare duality makes use of the Hodge duality, basically to say, hey, there's an isomorphism between k-forms and n minus k-forms, right? So Poincare duality and this is proved in Rentlen in some detail, is that the Deram cohomology of the n minus kth Deram cohomology over the M is isomorphic to the dual of the kth Deram cohomology of M. And I think you can kind of guess that this is a combination of like the what's it called, the lemma, Reach lemma, I forget, and the fact that the inner product I just erased, because so I can take a k form, I can get n minus k form, and then I can use that inner product to link the two things and get an isomorphism by that lemma. Anyway, but you know, those details are not terribly important to us. But you notice here that the dimension, what's the dimension? So here the dimension of this is the k minus, so like we have beta n minus k, this is remember the Betti number? So the n minus kth Betti number is equal to, well, what's the relation between the dimension of V and the dimension of the dual space of V? They're isomorphic, they have the same dimension, right? So the dimension of the dual space of the kth Deram homology is also beta sub k. So basically this is pretty cool. Once you've calculated one of the Betti numbers, you automatically get another one for free from Poincare duality. So for example, we had found before that for the sphere, right? what did we figure out the I forget, was it 1? Oh, excuse me. The Deram. Oh, I'm sorry. I'm thinking of the simplicial stuff, but well, I told you those are equal. So if you take that other theorem into play, so the 2-sphere, right? What was this was what? This was R? Is that right? I'll take H lower 2, the homology. What was the homology? What was the H2 for the sphere? Tell me the page number.
It's 133.
Page 133 on Redland.
Because if there are n spheres.
Okay, but for 2 spheres in particular, now here M is equal to S2. Now what is the dimension of the sphere as a manifold? Yeah, it's a 2-dimensional manifold, right? So in this context, what k am I looking at here? 2 minus 0, right? This is for k equals to 0. So this would be R implies that, the Deram cohomology, the 0th Deram cohomology of S2 is also the reals, because that's the only one. I mean, it has to be. If this is one-dimensional, that has to be one-dimensional. Well, by process of elimination, it has to be a reals, since in our setup. In other words, once we calculated this, you can go the other way around too, right? Once we calculated the 0th now we calculated the 0th homology, right? The other theorem I told you about in chapter 6 relates the homology to the cohomology. Now, the relation between homology and cohomology more generally is nice. I mean, things are really nice because everything's over the reals, and like Rentland mentions, you have to look at this universal coefficients theorem. There's much more to the story in the more general setup of algebraic topology. All right, but here we have some really nice relations between things. Anyway, so that's the Poincare duality, which is I think interesting. All right, well, that's all I have on that part of the course, and now I'm going to shift gears considerably, kind of considerably, and I want to talk to you about theorem of Frobenius and the problem of understanding differential equations geometrically, the jet space. How do we understand these things? And I'm a little bit I'm at that point in my thinking where I'm not sure where I should start, Joe's like, that's my cue to leave. I will allow it. Let's see here. Okay, so I can't use my computer. Curses. The appendix in Rentland's not bad. His appendix, what is it? Appendix F is on this whole sort of ball of wax. So I'll tell you what I'm going to do. I want to talk about some competing notions here. I don't want to do that. I can't make up my mind. So the test is due next Monday, right? The due dates on the homework I'm more flexible on. I gave you some, I tried to give you some suggested dates which I thought would be healthy for you, just in terms of getting stuff out of the way. But I'm willing to take the homework later. The test, though, I really do need Monday. Okay, so. And I would also encourage you that if you do the test, we'll make certain parts of homework 6 and 7. I mean, everything gets easier. Parts of that test are, especially the first 5 problems, maybe problems 2 through 5, they should really cement in your mind how the exterior derivative works, how it relates to vector fields, and I hope those problems aren't a drudgery. I think they should sort of really help things settle in. Okay, so here's some questions. Frobenius and maybe geometry Pdes is the wrong thing to say. I don't know. Well, what I want to do in part, though, is try to describe how we can take differential equations and sort of free them from their coordinate, their coordinates. And maybe that's hard to understand if you haven't had differential equations. But let's see here. What's a good place to start? R. Fine. No. Sorry, I've read too many things. I read this book, I read that book, and now I can't remember which one I want to start with. So I'm going to start with Cartan for beginners. It's for beginners, right? So so it's like, okay, so here's an example. Suppose you want to solve a system. Ux is equal to some function a, which is a function of x, y, and u, and u sub y, which is some function b of x, y, and u, right? So this would be partial u partial x. This would be partial u partial y, all right? And suppose a and b are given smooth functions. You want to try to solve this differential equation. How do you do it? Oh, a and b are just given smooth functions. You know what? No, I'm not doing this. No. I'm not doing this. I'm sorry, guys. Maybe I should have just started class like 20 minutes late or something. Let's start more basic. How about this as an example? How about this? Consider x dx plus y dy equals to 0. Right? Now this you might see written in another way, right? You might see this written as what? Dy dx is equal to what? Minus x over y? Okay. Now how do you solve this differential equation?